Voltage references are ubiquitous, as they are required for nearly every function involving analog electronics, from bias to absolute measurement. In many circuits, only a gross level of precision is required, while some applications require extraordinary precision. In both cases, it is essential that the references be stable over time and environmental conditions. For some precision systems, a relatively inaccurate reference may be employed if calibration is effective and practical. This is only a reasonable solution if the system does not drift significantly. The limit of acceptable drift may be set by overall system performance, acceptable length of time between calibration, or both. The types of change in output voltage that affect product specifications include temperature coefficient, thermal hysteresis, long-term stability, and humidity. I'm Whelan, a design manager for signal conditioning products at Linear Technology. I'm going to explain how our new LS8 hermetic ceramic package can improve design and performance stability. The causes of drift in references are largely related to the environment. The most commonly considered drift element is temperature drift. In general, voltage references are designed and manufactured for low temperature drift. As a result, output voltage changes in a predictable way over temperature, and an output voltage temperature coefficient is generally specified. Temperature coefficient is usually dominated by circuit design, so packaging has little effect. Where TC is dominated by electrical characteristics of circuit elements, the remaining drift characteristics are mechanical in nature. In a semiconductor IC, the semiconductor components are protected by a thin layer of glass through which mechanical stress may be transmitted. Further, the die itself will expand and contract over temperature and will deform due to mechanical force applied by the packaging materials. Within the die, metal traces sandwiched between layers of glass will also apply mechanical force. These forces may be placed into three categories. First is thermal hysteresis. As an IC changes temperature, the different materials, including plastic, metal, and silicon, all expand and contract differently. The result is a change in mechanical pressure on the die due to the thermal cycle. That change in turn causes a change in output voltage that is constant unless the IC is exposed to another temperature cycle. As with any hysteretic effect, if the temperature extremes remain constant, the output voltage will follow a repeatable curve versus temperature as the temperature is cycled. This is illustrated by the blue diagram. Note that the output voltage as measured at room temperature will vary between two discrete values depending on whether the previous temperature was cold or hot. In general, wider temperature ranges produce larger changes in output voltage. Depending on the design and materials, the output voltage may change by a few parts per million or several hundred ppm. In comparing the diagram at the top left with that at the bottom right, it is clear that the difference between the two discrete output voltages, which can be seen in the first plot, becomes vanishingly small in the second. The only difference is the IC package, in this case SAW-23 in plastic compared to LS8 hermetic ceramic. When assembled in this open cavity ceramic package, a voltage reference can easily produce stability over thermal cycles that is improved by at least 2 times compared with a plastic package. Long-term stability, often referred to as aging, is a behavior where the output voltage changes over time with no change in conditions. With most voltage reference ICs, there is a relatively large initial change in output voltage in the first few hundred hours, followed by an ever-decreasing change that becomes infinitesimal in a few thousand hours. As product specifications tighten, and calibration periods lengthen, or calibration is eliminated entirely, there's a need for improved long-term stability. It has been widely assumed that the mechanism for long-term drift has been wear out or aging. However, this is unlikely for the types of devices and bias conditions used in voltage references. More likely, the cause is a combination of mechanical effects and mobile charge. It has not been well understood just how much is mechanical in nature. The high stability of products like LTC6655, LT1236, and LT6654 give a much improved understanding of the mechanical effects. As shown in the adjacent plots for the LT6654, long-term stability is improved by about a factor of 2. The most notable difference is in initial change during the first few hundred hours. The reference voltage in the LS8 package shows a small initial rate of change that decreases over time. This is a substantial improvement over the same IC performance in a plastic package. One often overlooked cause of drift is relative humidity. Plastic mold compounds absorb water. As humidity changes, the pressure exerted on a silicon die by the plastic package changes, temporarily altering the reference voltage. The time constant is on the order of several hours, and the change can be in excess of 150 ppm, as shown here for the LTC6655 in plastic MSOP. The effect is shown at constant temperature, so systems can be susceptible even in temperature-controlled environments. Here, the advantage of the LS8 package is its hermeticity. With the hermetic LS8 package, humidity has no effect on the silicon die. However, the PC board layout is critical, as water is absorbed by FR4, which can swell and apply mechanical stress to the IC package. Methods for reducing mechanical stress on a PC board are described in Linear Technology's Application Note 82 and include specific board placement as well as adding cutouts around the reference IC. Where Application Note 82 describes a 3-sided cutout, removing FR4 from all 4 sides, as shown here, while leaving the corners intact can give similar or better performance. The result is decreased shift from more than 150 ppm in plastic MSOP to around 30 ppm in ceramic LS8 for the LTC6655. It is clear from the data that position on the PC board has an effect on the mechanical stress as well. The traces in red show that none of the ICs in the center row of the PC board shift by more than 10 ppm, despite exposure to a change in relative humidity of more than 60%. Other units shift similarly, but they are more likely to shift more as the distance from center increases. Finally, the LS8 package is similar to a QFN package. This type of package is very common in both plastic and ceramic. It's surface mount, eliminating the need for through-hole mounting. Assembly and rework should present little problem, and the size is substantially smaller than metal cans or other ceramic packages. In conclusion, the LS8 package has significant advantages in stability over plastic packages and in size and ease of manufacture versus other hermetic packages. For additional information on these products, visit linear.com, where you'll find the datasheets as well as additional information about voltage references. Thank you for watching.